Welcome to a tutorial on the high-pass Butterworth filters. Okay, so let me just tell you that the high-pass Butterworth filter, so whenever we talk about high-pass filters, okay, the Butterworth filters especially, well, they are basically characterized by this sort of a transfer function, okay? So that is h of omega, let's just take its mod value, okay? That's going to be equal to, well, a0 divided by root over, since it's a mod value of this thing, okay, so 1 plus that of omega 0 by omega whole to the power 2n, okay. So this particular expression that you can see over here is basically referred to as the high-pass Butterworth filter transfer function, okay. So this is basically referred to as the well, transfer function. I'll just write it down over here. Okay, now let me just tell you what each of these variables basically stand for. Alright, so here first of all we're taking omega. Now, you know, basically whenever we're discussing about any kind of filter circuit, okay, so we should always keep in mind that we're basically working with the frequencies. So here omega actually refers to well, the angular frequency, not actually the frequency, but it's the angular frequency of the input AC signal to the filter, okay. So this is the angular frequency of the AC input to the filter, okay, to the corresponding HPF, that's the high pass filter, right. And over here, this particular term, that's omega 0, okay, this is the you know all sorts of high pass filters have a certain cutoff frequency which is known as, basically as the lower cutoff frequency, okay. So that's basically known as the lower cutoff frequency. So this is exactly that particular value that we are talking about over here. So if you all would basically try to remember a bit, then well, the lower cutoff frequency is actually that very point, or rather that very frequency above which the filter's gain basically increases, right? So that way this cutoff frequency actually demarcates the filters, I mean those electrical signals that the filter is taking at the input. It basically demarcates that which of the frequency signals would be just passed to the output by the filter and which would be attenuated. So it just demarcates the basically boundary between the signals that are to be passed, okay, or having the frequency above that of the cutoff frequency, and those that are to be attenuated that lie below the cutoff frequency. Okay, so that's basically what the high pass filter does. It just lets pass the frequency signals above the towards its output, of course, that are lying above the cutoff frequency value, and attenuates those below it. So here omega 0 basically refers to as the the lower cutoff frequency. Okay, I'm just going to write that down over here again for your convenience. So this is the lower cutoff frequency, okay, of the corresponding HPF. And apart from that, we also have here another variable that you can see as a0. Well, this particular term, that is a0, is actually referred to as the DC gain, okay, DC gain of the HPF, that's the high pass filter. Now what I mean by the term DC gain, now DC of course is actually a condition, or rather some sort of a signal, okay, which doesn't have any frequency. So for for a signal, well, so in that case basically whenever we don't have any sort of input AC to the high pass filter, whenever we're not applying any sort of input AC signal to the high pass filter circuit concerned, then the maximum amount of gain that the filter circuit can produce, okay, that is basically referred to as a0, okay. So that's why we just call it the DC gain. Now you can also call it this is also the maximum gain that is basically offered by this high pass filter circuit, okay, to any corresponding AC signal, okay, applied to its input lying above the lower cutoff frequency. Okay, so this is also the you can also call it the maximum gain. Okay, so maximum gain or rather maximum passband gain. That's better. So let's talk about the passbands a little later. Okay, so I'll just write down over here, so you can just keep in mind that this is basically referred to as the maximum passband gain. Okay, now apart from that, we have another variable, that's the n over here. So this particular term n is basically it's basically a positive integer. Okay, so it's basically a positive integer that we have over here, and now this particular positive integer is referred to as the order of the filter. Okay, so this is basically referred to the order of the corresponding HPF, that's the high pass filter. So it basically determines the order. Okay, now the question is, how does the order basically affect this particular transfer function expression that we have over here? Okay, but in order to know that, we first have to go through its frequency response. So basically the frequency response of this sort of filter basically would look something like this. If you'd have this particular graph over here with the transfer function, plotted on the y-axis, and here we just plotted with respect to the angular frequency of the input AC signal to the corresponding high-pass filter. Then of course its characteristic or frequency response would basically appear something like this, as I'm going to show you over here. Okay, or rather, let's just modify it a little bit. Okay, so that's better. So here, as you can see, well, we have this sort of a a response curve for a high pass filter. Okay, now you can see that over here, that as the frequency basically goes on increasing, well, until it basically reaches a certain point. So we would just call it the lower cutoff frequency. Okay, and that is basically characterized by omega 0 over here. So at this point, at the lower cutoff frequency, what happens is that the gain, the gain of the corresponding filter basically falls down to 1 by root 2 times its value. Okay, so I'll just come to it a little later. So before that, I just need to show you the passband gain, without which I'll not be able to do that. So just hold on for a second. So here, as you can see, well, let me just point out the passband over here. So what the filter basically does is that, well, since this is the lower cutoff frequency, the filter, let's pass those frequency components that lie above this, above this lower cutoff frequency. Rather, the lower cutoff frequency will be, I just drew it in the wrong place. It'll be a little up above the frequency axis. Alright, so that looks good. So now let's just point out the passband over here. So as I said, above this frequency, all the frequency components are basically well passed by the filter towards its output. So this region, this particular region is basically the passband, or the range of frequencies which can be passed or outputted by the filter. So that are just let to pass through the filter towards its output. So I'm going to just write it down over here. So this particular area represents the passband. Right. On the other hand, those frequency components below that of omega 0, that's the lower cutoff frequency, well, they do not suffer, or rather they are not amplified by the maximum amount of gain by the filter, and they're suppressed. So you can see that those signals, those frequencies lying below that of the lower cutoff frequency, well, they are just suppressed or attenuated by the filter by providing lower amounts of gain. So you can see that as you go below that of the cutoff frequency, so you can see that the gain basically decreasing. So this area, that's why, is referred to as the stop band. Since the frequency components lying over here are basically attenuated by the high pass filter. So that's the stop band. Or rather, this should be brought a little bit more towards the side. Just hold on a second there. Alright, there you go. So that's the stop band and the pass band respectively. And of course, as I was saying, that, well, in the pass band, the maximum amount of gain provided by the filter circuit, okay, to those signal components, I mean the frequency components lying above that of the the lower cutoff frequency, is basically A0. So as the transfer function over here points out, that as I said, that this A0 is basically the maximum amount of gain suffered by the offered by the filter circuit to those signals having frequencies above that of omega 0, okay, above that of the lower cutoff frequency. So that's the maximum gain that the signals in the pass band would of course experience. And as I was saying, that at the cutoff frequency, okay, at omega 0, okay, especially the gain over here just falls down to 1 by root 2 times its value. So it'll be basically, the gain over here would be A0 divided by that of root 2. So this particular term is just basically known as the point over here is basically known, that is omega 0 basically is known as the 3 decibel point, because if you just happen to plot this gain in the decibel scale, okay, then you'll find that the difference between the maximum gain and the gain at the cutoff frequency is about 3 decibels, right? So that's why this point is basically referred to as the 3 decibel point. Okay. Now, if you all are basically intrigued as to how we can relate this frequency response to the transfer function over here, then I might just help you out over here. That, well, let's just take for example that the input the input AC to the high pass filter has a frequency equal to 0. Okay, so whenever it's equal to 0, that is omega is equal to 0 basically, so that's the condition when omega is equal to 0, then of course you can see that the entire denominator over here would basically become infinite. So as a result, the transfer function would have a value of equal to that of 0. Okay, so basically you can see that at the at a frequency equal to 0, omega equal to 0, the gain, okay, suffered by the corresponding input signal is basically 0. So you can see that there is no signal over here. It's basically 0. And now if you just put the value of omega equals to omega 0, that's at the cutoff frequency. So if now omega is equal to that of omega 0, then of course the value of the transfer function, that is gain, would obviously be, it'll be A0 by that of root 2. So the same thing that we obtained over here. And then finally you can see that for omega, if omega is tending towards infinity, okay, if omega now tends towards infinity, then we shall find that the gain of this transfer function, the value of the transfer function would of course be nothing but that of A0. So that's, as I said, the maximum gain at those frequencies way above the lower cutoff frequency. So that's exactly what we have over here. And if we just corresponding, we just illustrated the condition for 3 points basically to give you a rough idea as to how we just relate it to the transfer function. But if you happen to experimentally find out the curve, then you shall see that it basically has a shape that is similar to what I've just shown over here. Okay, so now keeping that in mind, the question is now that why is this referred to as a Butterworth response? Or rather, why is this filter referred to as a Butterworth filter? Well, that's the reason. In order to explain this cause over here, I have to say that you need to take a good look at the pass band and the stop band. Okay, so Butterworth filters are basically a certain category of filters. Okay, now Butterworth filters are basically used in almost the major portion of electronics that are being used nowadays because of 2 reasons. Well, one is that they are just simple to design. Okay, so Butterworth filters are basically simple to design. Okay, and also for its flat pass and stop bands. Now, what do I mean by this point? So you need to look over here in the characteristic once again. So you can see that the stop band over here doesn't have any sort of glitches. Okay, it's it's almost flat. We can say that the transition is quite smooth and it is flat without any glitches. And also the pass band is correspondingly flat. Okay, now this is actually the real, I mean the practical experimental sort of curve that I've just drawn over here. But theoretically, it's basically theorized that the Butterworth curve should be, for a high pass filter at least, it should be something of this type. Okay, where this would be the pass band, and here would be the lower cutoff frequency. Okay. There you go. This should be the pass band. So this is what the Butterworth filter will, theoretically look like, and this would be the stop band. Okay. But actually, whenever we just try to find it out for certain circuits experimentally, a lot of factors just come in, and that's why the curve has a little bit of curved nature, as you can see over here. Okay, so this is basically the theoretical conception. Okay, so this is basically theoretical concept about the Butterworth filter. So, but practically it happens somewhat this way. But now the thing is that, well, this curve could approach the theoretical curve only if the value of n here increases. So what is n? N is basically the order of the high pass filter that we're discussing over here. So if n is equal to if it's the value of n is basically increased, then the curve would basically have a steeper sort of slope. Okay, so I'm just going to illustrate that over here. Okay, there you go. Now you can see that, well, we have three colors of curves over here. So the blue over here represents the condition when n equals to 1. Okay, the yellow for that of n equals to 2, and the red for n equals to 3. So whenever n equals to 1, the high pass filter under discussion is basically a first order high pass filter. Okay, and then for n equals to 2, it is a second order high pass filter, and basically for n equals to 3, the filter is basically a third order one. Okay, so now that said, we can basically also illustrate the nature of the transfer function over here. So for a first order high pass filter, the transfer function would basically would have a value basically look something like this, as I'm just going to show you over here. That's going to be a0 divided by that of root over 1 plus we got, well, omega 0 over here, okay, by omega whole to the power 2. Okay, so since n equals to 1, so we have the transfer function changing this way. Okay, now for a second order high pass filter, on the other hand, the transfer function would basically, well, have an expression looking something like this. It's going to be root over 1 plus that of omega 0 by omega to the power 4. Okay, so since it's since the n over here is equals to 2, okay, and now for third order high pass filter, well, h of omega basically looks something like this: a0 divided by the root over 1 plus omega 0 by omega whole to the power 6, since n equals to 3. Now we had here omega 0 by omega to the power 2n. So whenever n is equals to 1, we have it to the power 2. If for n equals to 2, to the power 4, and for n equals 3, we have it to the power 6. Now what happens is that we can see that as the curve over here basically steepens, okay, now this is basically the slope over here basically represents the rate of change of gain whenever we just approach closer to the lower cutoff frequency. Okay, so for the case of n equals to 1, the rate at which the the first order high pass filter basically has a rate of change of its gain of equals to, well, 20 decibels per decade. Okay, so, or rather, I'm just going to write it down over here. So this has a rate of gain change at, well, 20 decibels per decade, right? And for the second order filter, the rate of gain change is about 40 decibels per decade. Okay, so this is double of what we saw for the first order. Okay, and finally for that of the third order high pass filter, okay, the rate of gain change is about 60 decibels per decade. Okay, so we can see that, well, the gain basically increases by 20 decibels for each of the orders. Okay, now we can, well, have even higher orders of filters, and that could be basically obtained by increasing sufficiently the circuit complexity. And well, it also depends on how many filter stages we want to cascade together. So we can basically cascade first and second order stage to produce a third order stage. And now this way, if we just go forward and cascade 2 second order stages, we can get a fourth order, and so on. So this way we can just basically increase the order of the filter that we I mean the high pass filter that we basically want to design. Okay, and whatever we do, the characteristic happens to get modified upon increasing of the order somewhat this way, as I've just illustrated over here. So also note the fact that as we just go on increasing the order, you can see the characteristic curve, I mean the frequency response curve, approaching the sort of theoretical curve that we just thought about for a Butterworth high pass filter. Okay, so we can just see that its nature basically approaching the theoretical curve that we had previously thought about. Okay, so that said, we just come to the end of this tutorial video. Now we're gonna see you next in the forthcoming tutorials, and till then it's just gonna be a short goodbye for now, and thanks for watching.